Why do impedance transformers come in 49-to-1 or 64-to-1 configurations? Well, let's look at the circuit of an impedance transformer. We have the transformer here with the primary and the secondary windings. And then over here, we'll have some sort of resistance, which is, call it Z2 or Z load. And this is voltage 2. And over here, we have voltage 1 between this point and this point. Voltage 2 is between those two. And we consider this impedance 1 or inductance 1 and this inductance 2. Between these two fellows, we have a coupling, a magnetic coupling. So let's do our circuit analysis. We have V1 equals to L1 di1 dt plus M di2 dt, where this right here is because of the magnetic field that's created here and generates a reinforcing EMF. V2 then, in other words, this voltage here, again, we're looking at I1 and I2. This one becomes L2 the I2 dt, in other words, the current I2 there in the second circuit, plus M the I1 dt, and this is where that cross term happens there. And then, of course, we have our Z2 V2. Okay, now this voltage right here is 0, and we can say now the following. If we assume that we have a current proportional to e to the I omega t, then we can say that V1 equals to L1 times I omega I1 plus M times I omega I2. Similarly, we can say that 0 equals to L2 times I omega I2 plus M times I omega I1 plus Z2 I2. Remember, we have the I here as the imaginary constant, and the currents are labeled with a subscript, so that should remove any concern. We can then say 0 equals to L2 times I omega plus Z2 times I2 plus M times I omega I1. Then this implies that I2 is equal to minus I M omega I1 divided by this term called Z2 plus I omega L2. Now, with this expression for I2, we can go ahead and insert it in this term. And what we end up with is the following. We say then that V1 equals to I L1 omega I1 plus I squared M squared omega squared I1 divided by Z2 plus I omega L2. And we can actually say that this V1 is really equal to I1 Z1, the impedance. So here what we can do is we can cancel I1, I1, I1 there. Then furthermore, we can go ahead and say that this goes to -1. We had a minus here in the front, so that's become a plus now. So I got one step ahead of myself there. And then what we have is that Z1 equals to I omega L1 plus omega squared m squared divided by z2 plus I omega L2. So that is our expression for impedance. Again, in an ideal transformer. Now, let's go ahead and go to the next step. We say that Z1 equals to I omega L1, and now we multiply times Z2 plus I omega L2, and that becomes plus omega squared m squared. And the reason we did that is so that we can go ahead and divide by Z2 plus I omega L2. Great. Now what we can do here is we do a trick by saying, let's multiply times 1. And for that 1, we're going to write 1 in a funny way. Z2 minus I omega L2, and the same thing in the numerator. Z2 minus I omega L2. Run out of space there. So when we do that, something interesting happens. We end up with Z1 equals to, well, let's go ahead and do this. We multiply this fellow times this fellow times this fellow. So let's start with the denominator. The denominator then is going to have this value, Z2 squared plus omega squared L2 squared. If you see that that cross term cancels out, and then that just gives us the square root of the first term and the square root of the second term, and with a negative sign, but then I times I is I squared, which is a minus 1, so that becomes a positive sign there. And in the numerator, we have something interesting. We rearrange this term right here, and we come up with omega squared m squared Z2 plus I omega L1 times, since we're multiplying this term times this term, we get the same thing as the denominator, Z2 squared plus omega squared L sub 2 squared minus this weird term, omega cubed m squared L sub 2. And we close the parentheses. So that's what we end up with. We can write that a little bit different, but essentially you have a real part here. That's the real part. And then you have the imaginary part right here. So we have a real and an imaginary part. The other thing to notice now is that magnetization, through a result that we're not going to derive here, is essentially equal to, in an ideal situation, the square root of L1 times L2. If you're not in an ideal situation, you start with a kappa for, a factor. This implies that, of course, m squared equals to L1 times L2. Now we rewrite the upstairs with this finding right here, and we end up with omega squared L1 L2 Z2 divided by our friend here, Z2 squared plus omega squared L2 squared plus I times this expression here. Let's go ahead and do that, and we'll go ahead and do this. The downstairs, or the denominator, Z2 squared plus omega squared L2 squared. And upstairs we have omega L1 Z2 squared plus omega squared L2 squared minus omega cubed L1 L2 squared. Great. So that really is our main expression for impedance now that we've gotten rid of this magnetization variable by decomposing it using this formula right here. So that's our expression for the impedance. It's quite a mess. So let's make an approximation that's going to make it very, very useful. Specifically, let's talk about it. If this term right here is much, much larger than this, then we can say this term can be neglected and we're only left with this term here. And then similarly here, this term right here predominates and nukes that guy right there. So compared to this guy that's going to be very large, this term is very small, so we can neglect it. Similarly up here, so the z sub 2 squareds pretty much go away. And we end up with something interesting. Let's write it down. We say that z1 equals to omega squared L1 L2 z2 over, remember, we are deprecating c sub 2 squared, so we end up with omega squared L2 squared, and then plus I, the imaginary constant there. And the numerator is going to be complicated, but the denominator is going to be relatively straightforward. Again, omega squared L2 squared predominates, so we leave that one alone there. Omega L1 now multiplies omega squared L2 squared. And this one here is minus omega cubed L1 L2 squared as before. Now we can do some cancellations. This guy right here cancels here. One of these fellows cancels him, so that becomes simpler. And then over here we can say that these two omega squared L squared cancel, so that one goes, that one goes. And over here we cancel 2 out of 3 there, and we cancel this term right here. So then, and of course these guys go away. So then what we're left with is the following. Z1 equals to L1 over L2 times Z2. Now, what happens over here? Well, let's work it out. We have I times omega L1 minus, the only thing that's left over here is omega L1. So, of course, that goes to 0. So, Z1 equals to L1 over L2 times Z2. That's an intermediate result, so we won't put it in a box right here. Now, what we're going to do here is we're going to take an aside and look at something that joins the number of turns to the inductance. And what we can say here, starting with Maxwell's equations, del cross E minus B dot, we have the electromotive force is equal to minus N times d phi dt. And the electromotive force, or the inductance, is defined as the electromotive force equals to minus L times di dt. We're not deriving these right here. This is essentially a statement of this fellow right here. So that is linked to that one. And this one right here, a definition that makes sense. When the current changes in an inductor, we end up with an electromotive force opposing the direction of the magnetic fields there. So that's good. Now, these two, of course, can be set to equal because they're both electromotive forces. And what we end up with is, let's leave that one right there, and we can see it right there. And then we have N d phi dt equals to L di dt. The negative signs have canceled, and we've just set those fellows equal. This implies that N d phi equals to L, no negative sign there, L di. What we've done there is pretty much done away with our dt's, their differentials there. So therefore, N d phi di equals to L. That's another intermediate result. Let's go ahead and put that one there. And then we'll also put a little dashed result there. So with those two intermediate results, then we're getting close to the final steps. We look at the mutual inductance. Remember, this is the cross term between one end of the transformer and the other one. And specifically, we're going to look from coil 1 to coil 2. And we notice that this is called M21 equals to N2 d phi 21 di1. So it's the magnetization created by current I sub 1, and that's the flux that joins the transformer. And similarly, we have, well, as a matter of fact, let's go ahead and notice now that we have an expression for d phi di. So what we can say is a N2 times L1 over N1. And that comes from this result right here. D phi di is equal to L1 over N1. So that's that. That's M21. Similarly, we have the mutual inductance from coil 2 to coil 1. Remember, we have this transformer that's inducing fields on the other coil, and this over here is inducing a field on this other coil here, on the first coil. So then what we have is M12. That one is, like before, or similar to before, N1 d phi 1, 2 here, the I sub 2, because it's created by the current I sub 2. This then becomes, using our previous results like before, N1 times L2 over M2. Great. Now what we can say is these two are the same. In other words, they're equal to each other. Why can we say that? Well, we assume that the coupling is the same with respect to either coil. So there's a symmetry involved, and these definitely are strongly coupled. So this is our final step. N2 over N1 times L1 equals to N1 over N2 times L2. This implies that N2 squared divided by N1 squared equals to L2 over L1. Therefore, going back to our other intermediate result here, which we needed to have L1 divided by L2, Z1 equals to N1 over N2 quantity squared times Z2. This is the result that we wanted to get to, and it relates the impedance transformer's characteristics of changing the impedance from the input to the output based on the windings of the toroid, or based on the windings of the transformer. N sub 1 would be the windings of the primary, N sub 2 would be the windings of the secondary, and the ratio of that number is what actually gets squared. So for example, we have N1 equals to 14 and N2 equals to 2. So that's 14 divided by 2, that's 7. 7 squared gives us 49. Therefore, we have a transformer that goes 49 to 1. Similarly, we can have other ratios. You can have 8, for example, and pick an n1 and an n2 such that you get the ratio of 8. 8 squared is 64, 64 to 1. So that's the reason for having that squared. That's where the squared comes in. And again, we started from the circuit analysis and we've come up with this relation. This concludes the video.